a quick intro, and then we'll go around the room as well. Noel Moran, I'm with SEH, Sustainable Energy Hawaii. We're a nonprofit. We're focused on empowering our community with information so that we can actually, make an efficient transition to a more sustainable energy future. We host this really informal session every Friday, or we try to most Fridays. And at times we have special guests, folks who knock on the door and have maybe some interesting solutions. And that's the case we have today. So team, I'd like to introduce you to Scott and Abhay, and I'll give you guys the opportunity in a moment here to introduce yourselves and also the technology that you're proposing. Shall we just go quick around the room, just name and location? Virginia, starting with you. I think we already
Virginia. And I'm in California, but I support media for Citizens Climate Lobby Hawaii. So I like to give publicity to climate solutions. So anything you can kind of pass on, then I could pass it on.
Yeah, Virginia has a huge. Is it fair to say you have a huge list now of people that submit or subscribe to your?
Well, it's not. It's about 50 people.
Still. Keith?
Hi, Keith Neal. I make my home in Waimea on the Big Island. I'm the policy lead for Sustainable Energy Hawaii.
Thanks, Keith. Jason?
I'm Jason Hershey. I'm calling in from Golden, Colorado, but I will soon be moving to Hilo, Hawaii at the end of the year. My partner will be starting as an assistant professor at Hilo. And today was actually my last day at the National Renewable Energy Lab. So I'm looking to get involved in the energy industry in Hawaii.
Yeah. Great. Thanks. Mitch?
Yeah, I'm Mitch Ewan with the Hawaii Natural Energy Institute, where I'm the Hydrogen Systems Program Manager. What that means is I build hydrogen gas stations, and my last surviving one is on the Big Island, right beside right beside the airport at Nelha.
Thanks, Mitch. Yeah.
Hello, everyone. I'm Diana, or Dia. I'm in South Kona. I'm an architect and sustainability consultant in different scales, home and urban design, and I'm very interested in sustainable solutions in general.
Thanks, Diana. Gary?
Hi, I'm Gary Rosenberg. I'm a regenerative farmer in Curtistown, Hawaii, and I've spent a lot of years thinking about how can we develop a new agricultural system which will serve to serve as a form of eco-remediation and sequester carbon.
Thanks, Gary. Vicki, thanks for joining us. I hope you're recovering well.
I am. Thank you very much.
We're just going around the room doing quick intros, and we'll introduce our guests. You want to do a quick intro on yourself as well?
Yeah, I'm Vicki Newman. I'm a resource efficiency manager with the 9th Mission Support Command Army Reserve in Honolulu. I'm a CEM, and I deal with pretty much all things energy and water for them in the Pacific Rim region. We do microgrids, water, rainwater harvesters, recirculating wash racks, booster pumps for water pressure, and try to turn the HVAC down to a reasonable temperature and not air condition to 62 degrees like they want to do here. But in general, I do a lot of paperwork and projects and get really strange government missives lately.
Thanks, Vicki. Glad to have you back.
Thanks.
Gentlemen, I will turn it over to you. Have you do a quick intro. So I believe you have a presentation. I'll ensure that you can share as well.
You talking to me, Noel, or who? I missed the first part.
Yeah, I'm turning it over to you, so you can do a quick introduction, and then you can share.
Okay, all right, sounds good. Hello, everyone. It's nice to meet you. I'm from South Carolina. My name is Scott Cummings. Our company name is Creek Tides Energy and Power, and we have multiple patents out across the globe. And our turbine is something that we are looking for to help people that's opening up an untapped potential to make energy in our slow moving oceans and tidal currents and 0 to 3 to 4 mile an hour water currents where the current fixed blade technologies have trouble even rotating in. I've been in the industrial electrical side all my life, 30 years in the powerhouse as a lineman, journeyman electrician, 230,000 volt substation electrician, and also into a journeyman electrician in a coal-fired power plant. And they shut that down because of what's going on today. And now I work as a measurement technician for a natural gas company, and I am the measurement technician, and we deliver the 1200 psi natural gas to power stations and stuff like that. So I have a broad view of how power is made and how it's delivered, and this turbine opens up a broad view of a new way of making energy. And we're just trying to get it out in the world. It's a very simple process. Very cheap to make. It's very efficient. It's very scalable. And we have proven technology now through the Department of Energy. And Abhay was actually one of the guys that did the high fidelity CFD modeling at Southwest Research Institute. And he has come on board to be my partner in this. And he sees the great potential behind it. And he now works for Baker and Hughes until we can get this up and going. So my background's in the electrical side and now the renewable energy side, and we are very close to getting to commercialization. And we just got this project, $1 million grant to go into Alaska to make energy under 3 foot of ice in the Yukon River, which has never been accomplished before, in 0.6 meters a second to 1.5 meters a second, which is basically 1 mile an hour to about 3 mile an hour. And that is just about every tidal current river in the whole world. And y'all's water currents, we have done some research, Noel, and we have found published papers where fixed blade technologies are not what's out to help y'all in y'all's area. And that's the reason we want to get in touch. And we're very grateful that each and every one of you are here tonight with us. And we just want to say thank you. And my partner is Abhay Patil, and I'll let him introduce himself, and we'll take off with it. You there, Abhay?
Yes, I apologize. Hello, everyone. I'm Abhay Patil. I first came in contact with Scott while I was working at Southwest Research Institute. While we submitted our first application to TMER program that's being funded by Department of Energy. And first time when I saw this turbine, I was like, yeah, this is an interesting solution because hydrokinetic, tidal, marine energy resources in general, they are very slow. Like, means between 0.5 to 1 meter per second. They are like surrounded, means majority of the, when you think about Alaskan, Hawaiian shores, the tidal energy is pretty much in between that. But the current focus for the hydrokinetic and tidal developers is basically going into faster currents. Going into faster currents means also actually higher cost. Cost of developing a power plant in aggressive environment is very high. And when you think about developing the hydrokinetics, basically nothing is off the shelf. Everything is custom made. So that makes it really expensive, plus operational and overall maintenance cost is very high when you think about high hydrokinetics, high velocity hydrokinetics. And high, I mean to say here is like more than 1 meter per second. But when you think about, when you go in the other direction, when you think about the current less than 1 meter per second, if you find a way to harness this energy, of course, you will need a bigger systems, but overall reactions on the system is significantly lower. That also keeps overall structure and the cost associated with the design is also cheaper. And if you find the solution that can reasonably harness the energy, without any significant skill involved in developing the technology, that further reduces the cost. So ultimately the objective is to how to harness the energy in the cost that basically is affordable to. We are mainly focusing on the remote communities where actually it is high. So it's lower than what actually they are currently paying. But can we go somewhere in between what actually is the mainland compared to, like, say, communities like Hawaii or Alaska? Alaska is in forefront of the weather challenges. Basically, nothing works there. So our primary focus is in Alaska, and we are getting some traction there. Basically, we own one funding opportunity from DOE. Will be demonstrating this turbine, reactive reversible blade turbine, under the ice, where the velocities are about 1 to 1.5 meter per second. But when we started, actually, I strongly believe that Hawaii is one of the market where actually this can make a difference. Majority of the focus is on the wave converters. That makes sense because currently traditional turbine, they don't really work. But when you think about this turbine, this is the solution that will work in Hawaiian currents. Either you think about the tidal, you think about the small ocean currents, or you think about the creeks or the rivers, right? So we'll just show you how it works. I honestly, I didn't get a chance to prepare it well. Today's my birthday, so I was out. But I'm going to try my best to help you understand what we're trying to provide here. Can you see the slide?
Yes.
Yes. So I'll directly go into the problems. I already discussed about the traditional problems with hydrokinetics, but when you compare that with the wind energy, say, the traditional utility grade wind turbines, their threshold limit for the wind, like the generation, is about 3 to 6 meter per second. And that pretty much coincides with between 0.5 to 1 meter per second water current, just based on the density of the water, that the fluid power overall coincide with that. But due to the challenges with the hydrokinetic energy or tidal energy in the slow moving water current, it never developed at the pace when you compare with the wind turbines, right? But again, when you think about the means, we're mainly focusing on the Alaska, where actually the velocities are between 1 to 1.6 meter per second. And we did our techno-economic using this turbine, and it seems like this is one of the viable solution when you think about this turbine. It has a potential to reduce more than 30 to 35% of current electricity they are paying using traditional fuel, just because it's really simple in design. Another issue, again, when Scott mentioned that fixed blade turbine, that doesn't really work. So this is one of the solution we're targeting. And another option is, the regulatory processes. Means regulatory mainly focusing on the marine life and the migratory behavior of the fish and how that impacts. I think you guys are well aware. We are still trying to understand that part. But when you think about that, when you think about the slow moving currents, system is bigger, but it's in a way slower. So it really will not impact any mortality point of view for the marine life or any migratory behavior when you think about the turbine who is really moving slow in the slow moving currents, right? So these are some of the aspects we are trying to focus. And the turbine itself is it's called reactive reversible blade turbine, because it's based on the principle that when the torque is, or the drag is positive, the blades are loaded. But when drag becomes negative, the blades are unloaded, and they balance in a way that there is a negligible drag around the blades. That means the drag is only impacted when the blades are loaded in the positive direction. So here I will show you this animation that we use in CFD, but Scott can explain better this technology. So here, these are the blades. Basically, they are locked here. Where it is actually locked is in the locker, the stopper, and at one point, the drag becomes negative, and it flips and goes back to the screen. And then after one point, it unloads from the screen, it's hydraulically balanced. So there, the negative drag is in a way negligible or very small compared to fixed blade turbine. That makes it really, turbine that can operate in slow moving currents. That was demonstrated using the first Timor grant Cricket received is using the Florida Atlantic University, where they tested this turbine under like 0.35 meter per second. And even using that current, basically it could rotate at one fixed angle to about 20% power coefficient in that slow moving currents. And we did further evaluation, CFD based analysis, and we realized that at different widths and different blade angles, the power coefficient changes and it increases the power coefficient. So again, it depends on your transitioning between the lift based and the drag based. When it's a slow moving current, we are still targeting the drag based turbines, but still there is a potential to increase the power coefficient to about 0.35, even in the slow moving currents. And when you think about this turbine, this is really simple turbine. You can see on the top, this is actually a picture from the Florida Atlantic University. The blades are simply connected pivots around the pivots, and there are stopper. They load on the stopper while actually in the positive direction. They unload when there is a negative drag, and they load on the screen. And then at one point of time, they release because there is a negative drag. They again hydraulically being balanced when they move from negative drag to all the way when it converts to the positive drag again. So this is inherently the basic principle. And also with the design of the turbine, you don't need a special design developing the aero or the hydrodynamic design or hydrofoil designs to generate the high CPs. We also evaluated that, it really doesn't make any difference. Simple flat plate can be very effective in generating the power, right? So structure, you will not need a significant investment in the structure because reactive forces are inherently really low when you think about slow moving currents. And you don't need skill labor to develop and assemble it. So overall cost, when you think about the overall cost of the turbine, including everything, we did a little bit techno-economic study, and it still comes out to be really close to like when it's mature about 10 cents per kilowatt hour to means 15 cents per kilowatt hour, something like that. It again, not accounting for inflation and all other factors, but the simplicity in the design, it basically makes a lot of difference. And when you are thinking about the slow moving currents, it can harness, just it's going to be bigger. But all the manufacturing side, material side, there are a lot of areas where actually we can reduce this cost in minimizing the overall cost. So, Scott, you want to add anything here?
Yeah, can y'all hear me?
Yes.
Okay, so pretty much what Abhay was saying there, this turbine can be built out of simple material, off-the-shelf stuff, and on the huge mega scale side, just say it was built out of I-beams. This turbine, just say it was 100 foot wide, 200 foot tall. You got a lot of area square foot on a blade, 50 foot wide, 200 foot tall in the ocean. You could imagine a 0.5 mile an hour water currents to force and torque that would be on that blade. And because if you did build a mega sized turbine, because it's under the water, you're in a whole different atmosphere, just like you're in space. So what you could do to overdo the friction or the bearing frictions on it, you could fill it with inner cores with that simple air. And you could float this system pretty much weightlessly, just like it's in the up in the atmosphere. And it would take all weight factor, friction, everything off of it. The way this turbine works that he was explaining, we've tested it at negative 18 degree blade widths, which is what you see on this picture where we started at. And we went to positive 18, positive 27, positive 36, 45, all the way up to 72 degrees. And our efficiencies just kept skyrocketing all the way to 72 degrees, which we could also do with wind, make a wind turbine out of it. But just say the positive 18 degree side, the way this turbine is working is it pivots on the outside edge of the circumference. So the bigger and wider the turbine is, it's like putting a cheater bar on a pipe wrench. As you know, if you put a pipe on a pipe wrench, it's easier to turn. And the way it rotates is simple, just like going in and out your door in your house. So you have this turbine blade locking on the front side of the 360-degree rotational, just say positive 18 degrees. And your force is hitting on the front side with no force against the back. So you got 100% force, and that blade is forcing water currents into the other blade in front of it. So what it's doing is it's creating a rotational force, and it's moving 360 degrees as it's going each segment of rotational force. And as soon as that blade senses water current force on the opposite side of that blade will reverse and change angles, and it will lock again on a screen system. We have something in our patent where the screen system can be part of this turbine, which controls the blade angle, which gives us double force outside of the sweep area. And it also gives us over 220 degrees of rotational force, whereas a normal fixed blade turbine would have drag on the other side of 180 degrees of that turbine of the shaft. We're getting 220 degrees of rotational force. And then as that, you got, in this picture here, you got 4 blades that's going to be forcing, and then all of a sudden that last blade, as you see, it's slicing through the water just like a fish, and his nose is going through the water. And the water current pressure is the same on both sides. So the blade would be hydraulically balanced. And the only drag that you would have, everything is force, rotational force up to 220 degrees. And then that 220, which, until it hits and locks again, is slicing through the water. And the only drag is the very tip of that blade. Whereas fixed blade, you would have 2 opposite angles, but because of the density of the water, it doesn't matter about the angles. They're 2 opposite angles, but the same density of the waters causes it to teeter-totter and not rotate in very slow-moving waters. This turbine here was tested at Florida Atlantic, like you said, in 0 to 1 mile per hour water currents. And we were in a negative 18, and we was getting 20% efficiency on that angle. So, and the turbine had no startup issues. As soon as a stick or something, you seen water flow, the turbine's rotating. So we have no issues with the slow moving water. And as the water speeds up, of course, you get more power output. But because this turbine turns so slow, the fish, it's going the same speed of the water. It's not a meat grinder in the water. It turns at a slow RPM, but with a very, very high torque, which gives you the power to turn a generator. And we can scale this thing from miniature sizes for kayakers, hikers to charge cell phones, computers, and creeks to sell on Amazon, all the way up to mega-sized turbines for powerhouses, for what y'all need. So the simplicity of it and the cost effective of it makes a big difference in what we're trying to do. And our ultimate goal is to just give power. I don't know if y'all are into desalination, but just like turning a generator, you can turn a water pump also and create desalination. I have another patent with a tower system. This turbine's part of that tower system. And one of y'all was Mr. Mitch, I think, was into hydrogen. You could even use this turbine system for capturing the water currents. And we have a wave technology side that we haven't even started testing yet, but this turbine could also use the wave energy to rotate with the water currents. So you're capturing wave energy and the slow moving water currents, and it will work vertically, horizontally, and it will work any way the water hits this turbine in 360 degrees, it will rotate. You don't have to pull it out and change it. Tidal currents if it's coming one way, you're forcing on one side. When the tide changes, it's just going to force on the opposite side, but turn in the same direction. So that's in a nutshell what it is. It works just like a door going into your house. It's that simple. We've tried to simplify it, but it's so simple. It is what it is, and it's doing the job. And with the grants that we've gotten from the Department of Energy, and doing the flume tank testing in 0 to 1 mile per hour, and the high fidelity CFD modeling, we calibrated from that, and it fell right in line with our CFD modeling with Abhay, and it has proven to be very efficient, very scalable, and very cheap to manufacture with unskilled labor, which will open lots of jobs in Hawaii. So, in a nutshell, that's pretty much what Abhay was saying, and I'll let him take over from here and explain the rest of it.
Yeah. So when you think about the turbines like that, this, and when you're trying to say initial how means we can generate the electricity using this turbine. So our initial thought was, if you are going to say generate 1 megawatt, like thinking about 10 kilowatt systems, 100 of them in a tidal farm, right? And this is very viable when you think about, slow moving currents somewhere actually near the shores, either in the tides or river in the creeks. Because when you go something like that, or this approach, say 10 kilowatt, multiple of them, in a way you are creating the manufacturing and the supply chain for this kind of design. Because this basically, it does not require any skilled labor. So this can be manufactured and assembled and actually deployed locally. Everything can be done locally. So that basically will also promote the local labor, and overall simplicity and running at slow rotational speed. The slow moving currents actually doesn't require the material with significant strength. So simple material with simple manufacturing solutions can basically work to overall develop the manufacturing as well as the supply chain units for this kind of design. So that's something we're actually envisioning. So this is just one demonstration. I just wanted to give an example. Say current velocity is 1 meter per second. When we're talking about 15 feet by 15 feet, it will generate about 2 kilowatt based on all the losses like the generator loss, gearbox loss, wake losses, everything. This is just based on the sheets created by the Department of Energy we used. And we just use the simple manufacturing, machining, and material matrix from the sheet, how much it will cost, what will be the LCOE. So LCOE comes around 0.09 to $0.1 per kilowatt hour. I understand this is too crude, and we have submitted one SBIR proposal in collaboration with NREL that focuses on the first part, basically developing the detailed techno-economic of how this turbine will actually work and what will be the cost of this turbine in slow-moving currents. But this just gives the layout of, okay, this is definitely technically, this is viable. We can generate the electricity, and what will be the cost, right, at this point of time. So there are going to be some divergence, it's not going to be the exact, but what we need at this point of time is, path forward to demonstrate it. We found that in Alaska, we're working with the University of Alaska, but Hawaii is in a way challenging because majority of the focus is on the wave energy. But when you think about this is a retrofit, or this can be replacement to wave energy converters, because it can effectively harness the tidal. Like wave is still not that predictable, but tide is really predictable. So it can actually rotation direction is same. So it can generate the electricity both way, no problem at all. And it can generate the electricity with higher energy density compared to the wave converters. But just because it was not there, it's changing the mindset or convincing people is going to be hard. Hawaii is going to be hard. We very strongly believe that. But getting the opportunity to demonstrate this, somewhere in Hawaii, just to show people that this will work, that's something we'll try to do. And this is what we're trying to, pursue. Scott found this connection, I was like, yeah, this is interesting, and means at least convey this idea to you guys and see how you can help demonstrate this. Because overall means when you think about the wind turbines in Hawaii or solar in turbine, this is definitely means viable compared to the current solutions. It just, we need some support or some direction. How do we demonstrate it? We strongly believe that this will work in Hawaii.
Thanks, Abhay. There are a couple of questions in the chat. Vicky had one for Scott regarding availability of any reference DOE report that can be shared. Is there any documentation available that can be shared?
Yes, of course. We've Abhay has already also with ASME. He's been to 2 conferences to speak about this turbine, and we actually won first place on Abhay won first place on the paper with ASME, and we have the teamer finished on the 0 to 1 flume tank, and we are finished with the high fidelity CFD modeling that we can share, and we just won the $1 million grant with Alaska, and so we should be able to share that also. And Abhay has all kind of information he could probably dig up for what we need. And there is a lot that probably more than what we could discuss tonight that we'd love to talk to you about with cargo ships to bring in energy to a port and drop straight into your grids. There's so much out here that we want to talk to y'all about, but we just won't have time tonight. But yes, we can share everything with y'all.
Yeah, you could, if you could share that with me, and I'll distribute it to the folks who are interested here. There was another question related to that, and that's any website. I was able to access your website, although access was not very intuitive.
Yeah. We have been focusing so much on research and development and writing grants. I've sort of let my website just go to the side, but we are definitely getting ready to update that. There's a video on there, the first one I put in the river, and that was in like a little over 1 mile an hour water currents. It was a little 2x2 turbine, and the website is creektides.com. So I wish I could send everyone a video. If you could send me everybody's, I could send you a video and you could share with everybody, on the simplicity of how it works.
Yeah, share it with me, and I will distribute to the group.
Okay.
And I think Paul just joined us as well. Paul, if you're out there, thanks for joining. Let's see. Was there another question? Oh, Keith, you had a question regarding
marine fouling. Yeah.
Yeah.
So anything in the ocean's alive. Well, all water bodies are alive.
Yeah. We do cathodic protection is what we use on our gas lines, Mr. Keith. I know boat motors, they have the anodes and all that stuff on them. There is a way that we could do cathodic protection on this. Dealing with Alaska, we have to deal with frazzle ice because the water currents are going to be 30 degrees. So we have to use UHMW stuffs, polymers over there because we don't want no ice to build up on the turbine for what they're looking for. But that's something that we have to figure out. As you say, everything in salt water is a challenge. But because of the simplicity and the cheapness of it, we feel like we could try to do a good maintenance. There's ways to do these where you could float them or you could connect them to poles and drop them in and out where you can lift them very easily on the big turbines. And that's just things that we have to work out. But I agree with you. It's something that everybody that deals with salt water has to deal with.
Yeah, this is the first turbine I've seen that the blades move.
Yes,
like that. I being a sailor, I'm watching these turbine blades do a jibe.
Well, these are turning slow, and we don't have no vibration problems. That's another good thing. It's safe for the fish and the wildlife, and it's actually interesting just to sit there and watch it just rotate. It's just simple, easy flow with the water, and the fish could swim right through it. And if we got the screen system that we could put around it, if a big palm tree floating in the water hits it, it would divert it. About like you see a football player playing football, they do that twist on the field and just roll around. And because it's round at 360 degrees, that 1 degree point on either side, that blade's it's just gonna roll like a log in the water and divert whatever hits it. And it washes itself off really beautiful as it rotates with the screen system. Any more questions? And the bigger this turbine gets, we've calculated also the cheaper it gets for the LCOE, because it's cheaper to build the bigger they come. And we can make energy start making energy at 0.37 tip speed ratio, or a little less than a half a mile an hour water currents. And I think y'all over there are around what, 1 mile, 1.5 mile an hour water currents for y'all's oceans.
Scott, I'd like to ask a couple of questions. I was watching as a sailor to what Keith just mentioned. I just want to understand, you're basing your theory on a combination of lift and drag, and you're getting essentially what I thought you were saying is 220 degrees of rotation in the energy providing sphere, and about 140 of drag of resistance against the system. Is that and does the shape of the blades, does that affect that? And have you tried different shaped blades to increase or decrease that? I was clear.
Yeah, we've tested the aerofall blades in the high fidelity CFD modeling, and for the cost of the blades, it wasn't worth the difference in the efficiency. And yes, we're getting right at 220, maybe a little bit more of 220 degrees, because when the blade reverses, it reverses in an opposite angle, which helps us capture the energy on the other side of the 180 degrees of the shaft. And once that blade senses the water current pressure on both sides of the blade, it hydraulically slices through the water just like a fish with no drag. So really the only drag you have is the thickness of the blade. It's not like an angled blade with a drag on the normal fixed blade technologies where they're all in an angle coming back. You got the opposite angle on the side of 180 degrees of the shaft. So we almost can say we don't have drag, but there is a minute little bit of drag, and that's what makes this turbine so special, is because we don't have drag. And the little bit we do have is the part where it pivots and the thickness, whatever the thickness of the blade. And that blade could be 50 foot wide, but it could be 6 inches thick. And you're only having 6 inches of blade just slicing through the water, if that makes sense to you.
I guess I was more asking in terms of Venturi effect and aeronautical shapes to increase the lift portion of your work.
Yeah. So when you think about lift-based principles, when in the positive direction, there is no noticeable change in the positive drag or lift. But when you think about the negative direction, that's where actually it plays in. Aerodynamic shape basically helps minimizing negative drag. And that's in a way basically actually increases your power coefficient. But good thing about this turbine is basically when there is a negative drag, it's just hydraulically balancing itself by rotating. So there is going to be some loss when it's actually flipping. But when you think about that negative drag that's associated with the fixed blade turbine, that's not there. So that is a positive side of the hydrodynamic shift, like the aerodynamic aerofoil or hydrofoil. But in this case, it's not really effective, because when you think about the negative drag, you really don't need it, because it will reverse slice itself and balance itself.
Have you been able to calculate the percentage parasitic losses from the electricity necessary for the hydraulics?
No, not really. You're talking about the overall parasitic losses from the hydraulic, right? Yeah, we did not at this point. Yeah, that's one of the things we want to do, but we did not estimate. Yeah, that part is in a way a little bit unknown.
Thank you. One more question. I think it's a very interesting design. I guess what I'm wondering is, I can see how this potentially gives you an opportunity to take advantage of slow moving water, but by changing the resistance curve, would not this same configuration also be appropriate in fast moving streams by lowering the resistance?
Yes.
It will require some changes in the blade angles because you do not want to slice it like that in the high moving currents, because that probably will induce additional losses, I would say. Again, unknown, but we have to think about a different approach of how we can actually optimize the blade motion in a way to minimize the losses, hydraulic losses, if that
So
makes
you're
sense.
suggesting that the turbulence created through the blade movement at some point creates a vacuum?
It will create some issues, I think, if you go to higher currents.
So what happens is we have to change the blade angles for whatever water currents we're dealing with, and we could make the blades, instead of say positive 18 wanting to capture a half a mile an hour water current, we got a blade that's half the circumference. And then if you want to go in faster water currents, we can make the blade say 72 degrees positive and make the blade narrower. It won't be as wide. And that's where we're getting the speed rotation for wind. That's what we're going with to make these turbines wind turbines also. And that tower system there is the other part of my patent I was telling you about. Just imagine that bottom part under the water, and the arms and flotation are big as houses, capturing y'all's 50 and 100-foot waves. And they're all changing. Just imagine there's hundreds of them all the way around that unit, pressurizing that tower. And you're dumping that water, pressurized water, through piston pumps, through a 48-inch line, sucking just like a straw, and you're dumping through a hydro generator right back into the ocean. And you have the turbines under the bottom and kick turbines capturing the water. And the inner cores we have in our patents, we can store hydrogen, and you could put a mini hydrogen plant underneath this, and you have all the power you need, all the pumping capacity, the water you need, and you could use these tower systems in the oceans for cargo ships, just like gas stations from point A to point B, from where they load and unload to fill up on hydrogen instead of using diesel generator. And you could use these also as transmission lines across the oceans and tie all the countries together with a DC power line, one cable, and use these as transmission lines also. But right now we're just discussing the turbine, but my other patent is this tower system.
Scott, do you think it would have application on a small private situation for somebody who has a slow-moving stream or river on their property, as opposed to a micro hydro situation, to be able to derive some power from a slow-moving stream?
Yes, exactly. That's what we're doing around here. Where I live I live 45 minutes from the ocean. We got tidal rivers. We got the longest Blackwater River called Eddystone River that flows one way all the time, and their water currents are 1 to 1.5 mile an hour all the time. And yes, we got different ways that we want to do this, where you could pull a turbine down the road just like you pull a boat, and back in, put a small motor on it, and deliver it to somebody's boat dock, and just tie it up like a boat and hydraulically drop it down. It's easy maintenance. Wash it off with a power washer every so often, and just plug it in straight to your house, right there where it sits. And you can just tie it up just like your boat and just drop it in and out the water with a cable system or hydraulics or whatever. Just trying to make it cheap as possible.
Let me know when you got one for sale.
Okay. Well, that's doable. It's very doable. And there's so many avenues that we could go down. And one of them is with the cargo ships, using a big turbine on the back of a cargo ship and hydraulically. Just imagine a cargo ship loaded with 50-foot containers, but they're batteries. And you got 6,000 on a cargo ship, and three guys could support a cargo ship, drive it off right where your current is, cut the engine off, drop the anchor, and lower this turbine in the water with two hydraulic arms off the back of the ship, and just let it sit there and troll like a fishing lure. And you charge five units at a time until you get that whole boat loaded with power. one 50-foot container will feed 200 houses for a day. So you imagine 6,000 and just pulling the turbine up, easy maintenance, pressure wash it off. That saves on the cathodic protection. You go into a port, you don't even have to deliver to take the containers, the batteries off, dump right into an inverter through a transformer, and dump all the power into the grid. But if you wanted to deliver them, you could deliver it just like they deliver containers now. And you could deliver these containers to every parking lot in the world with a SCADA system on it. It shows when the charge gets down, and you got electric vehicle charging stations portable that you're not even connected to the grid with. Then the SCADA system says, okay, we're getting low, deliver me another one. And you could have these cargo ships sitting out there all day long, just sitting still. Nobody can see them charging a whole system and come back and deliver them or dump them just straight into the grid, versus having one turbine here and one turbine here trying to support it. It's huge. It's more than the mind can imagine. As big as you want to think about it, it can be done for electric vehicle charging, desalination, hydrogen, and regular energy.
So, Scott, there are lots of people who are coming up with new designs for buoys. Some of them are 30-foot in diameter that are harnessing wave and tidal energy. So how do you respond to those people in that situation regarding your product versus those?
I don't think nobody's out there capturing these water currents. From what I've seen, these people have to be in the higher 3 to 4 to 5 to 6 mile an hour water currents to do this. I haven't seen a product out there yet making energy in a half a mile an hour, 1 mile an hour water currents. I haven't seen that. And our patents have been granted. And we've been at this since 2018. And I haven't seen this technology out there that's making for these slow moving water currents.
And when you think about wave energy converters, it's about what is viable when you think about especially wave energy converters when the tides are very slow or the ocean currents are very slow. That's basically the viable path forward. But when you compare with this device, because there was nothing as such so far, when you compare the wave energy converter like those big giant systems compared to, there was nothing there to compare, right? So this is basically one of the area, the gap we see, technological gap, where actually we need to understand that when there is a wave energy converter and we have this turbine there in the similar scenario, but it's actually missing the tides in the same application, same site, and how this compare with the wave energy converter. So that's something, the base studies definitely will give you some understanding about what will be the energy density that it can capture, what will be the power coefficient, what will be the cost. But trying to implement that and the way actually wave energy converters are being tested, test this system in the similar site that will basically give us the answer. But at this point of time, it's all about mindset. If you say that, hey, trying to convince people, can we do that? Basically, it will be hard to change that because there was nothing as such tested that's rotary in that environment, just because it doesn't work, fibrillated technology. So, yeah.
We have about 7 minutes left, and I'm just wondering if others have questions. Mitch, Jason, Vicky, anybody else? If anyone has questions for Scott and Abhay.
I don't have a question. I think it's really interesting. I have a couple of years ago dabbled in looking at wave power for desalination and generation of energy. The 9th Mission Support Command has sites in America, Samoa, Saipan, Guam, and we're all very close to the ocean, Maui and Hilo and Honolulu. And how do we get our resiliency up? And what you just commented on, that there isn't anything for low frequency or low flow water. And so this is really exciting. I also have fellow REMs that work at Quantico and other locations like the Chesapeake Bay would have a lot of need, and NAVFAC here in Honolulu Harbor, there's a large need to supply the ships or bring things in. And as you're talking about hydrogen fueling stations that are just self-generation stations that are permanently mounted out there where a boat can just pull up and refuel from is pretty exciting.
Yep.
So.
I mean, it's way bigger than the turbine, and we're trying to capture, because the turbine is the cheapest way to go right now, and we're trying to get tests. We really want to do more testing with the tower system, but the turbine is a crucial part of the tower system also. And this has been my step. It's been a long road, getting the patents and everything. I've been investing all this myself out of my retirement and my life savings, and it's been a long journey for me. And I've put everything in my whole entire life into this, and I really have faith in it. And I've had my hands on it. And now, after we got to the Department of Energy and the proof is in the pudding, now Alaska, we're just going to stick a generator on something we already know what it's going to do, and we should be ready to roll after that. And we would really love to come into Hawaii and give y'all power where it's already been published that fixed blade technology won't work. So we want to stab at it, and we want to try to come in and help Hawaii any way we can, because it's not about money, it's not about pride, it's about getting good, reliable energy and getting it from the resources where we don't have to buy coal, we don't have to mess with nuclear rods. You're not dealing with whether the wind's blowing or not, or the sun's shining and cloudy. You got 24 hours a day, 7 days a week, dependable current energy, and y'all have wave energy that will push this thing. Even then, say on the banks, on some place where you got your tides, your waves coming in, you got your undercurrents. So you're talking about everything. You're talking a spinning turbine with the undercurrents and the waves coming in, and you're talking a major power. And it's just a way of getting it there. And there's multiple ways: cargo ships, supporting them different ways, floating them, anchoring them. There's just so many different ways that we could talk about. And that's what we're trying to do. We're trying to figure out a path that we could come in and help y'all. And with the help with Hawaii and y'all's engineers and knowing y'all's water currents and y'all's lands and y'all's government, everybody come together as one and do what we need to do, and that's get energy. And we're willing to work any way we can with y'all. Anyway.
Well, we really appreciate that. And I'm sure there'll be subsequent conversations and discussions. Look for Scott, I'll coordinate with you to get the information. I'll pass it out to the team. I will also, like I said, I mentioned that Riley Saito with NELHA had expressed some interest, but couldn't be here today. I will just connect the two of you so you can have the conversation.
Okay.
And, in there were links that were shared. One of the links was to a page with a video that's about a little over a minute. And I would like to share that just to wrap this thing up. We have a 2 minutes left here. So let me just
crashing wave.
share. I'm sorry, was there a comment?
I started some link. Go ahead, please.
Okay. So let me go ahead and share. Let me know if you can. Can you hear it?
There you go. That's the first one I did.
Energy and Power proudly presents the reactive reversible blade turbine. This new patent-pending design provides an ingenious solution to hydropower generation from slow-moving currents like river, tidal, and ocean. Prior to our design, it has been difficult to harness the unlimited power from these sources due to the inefficiency of fixed-blade turbines. To solve this problem, the reactive reversible blade turbine features blades that pivot to capture the maximum force of the water current to propel the turbine, then pivot again on the backside to a neutral position, then slice through the water with almost zero drag as the blades return to create torque continually. This design marks a milestone for turbine development. It works vertically, horizontally, and bidirectionally, making it perfect for tidal applications. Visit creektides.com to learn more.
Was that you?
That's me. That video is my first video of the first turbine I made, 2 foot by 2 foot. That's my dad talking, y'all. It's touching to me. He passed away in the midst of me doing all this that he really enjoyed, and I got a video of him saying all that. And he's going to be with the Lord now, but I know he's praying for me and talking with the Lord about it. So, but yes, that turbine blades were 8.5 inches wide. That was on a negative 18 degree. That was in water current, so 1 mile an hour, maybe 1.2. As you can see the water flow, it wasn't turning fast. Look at the leaves and stuff. And I double nutted that 5/8 shaft, and I put both of my hands on it. And the 8.5 inch blade, 2 foot tall, I couldn't stop the shaft. That's how much power was on that turbine. So you imagine a 4x8 sheet of plywood, say 2 of us in a river, 1 mile an hour water currents. We could hold it with our finger pointing in, which is what it's doing when it's slicing through the water. But as soon as we turned that 4x8 sheet of plywood this way, 2 fellas couldn't, it would force us back. That's the key to this turbine, area square foot force. And the blade, that turbine, when it reversed, I didn't have a screen or nothing to lock the blade. It was just free flowing. But imagine that blade locking in a forceful position when it reverses. And that's how we're getting over 220 degrees before it lines up and slices through the water and then locks again. And that's it. It's just that simple.
Thank you. Scott and Abhay, thanks very much for this. I have this recording, and I will share the recording with the team, and also any information you have. And
we will get that to you.
Yeah, I'll make the introductions as well with Riley. Folks, thank you very much for joining. Really appreciate it. I know some of you are dialing in for way across on the other side, so it's pretty late out there. Really appreciate it. Thanks all. Have a great weekend.
Thank you, and nice to meet everyone. Look forward to more discussion.
Bye.
Aloha.
Thank you.
Take care.
Thank you.
Aloha. Thank you. Appreciate you.